Tonight, we're going to talk about something that's changing everything we thought we knew about the universe. The James Webb Space Telescope has been looking back in time, peering into the earliest moments of cosmic history. And what it's finding is making scientists very uncomfortable. Because the universe Webb is revealing doesn't match the universe we predicted. Galaxies appeared far too early, far too massive, far too complex. Black holes existed when there wasn't enough time for them to grow. The cosmic web was already woven when it should barely be forming. By the end of tonight, you're going to understand what Webb is revealing about the early universe and why scientists are confronting the uncomfortable truth that something fundamental is missing from our models. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. It all started in December 2021. A rocket lifted off from French Guiana, carrying the most powerful space telescope ever built, the James Webb Space Telescope. 4.5 tons of folded mirrors and instruments packed into a space barely large enough to hold them. Over the next month, it traveled nearly 1 million miles from Earth to a gravitational balance point where it could observe the cosmos without interference from our planet's heat. Then came the most nerve-wracking part. Webb had to unfold itself. A sunshield the size of a tennis court, deployed in a precise sequence. 18 hexagonal mirror segments clicked into alignment. Instruments cooled to temperatures near absolute zero. Any single failure would have destroyed the entire mission. But everything worked. And in July 2022, Webb sent back its first images. Scientists had been waiting for this moment for over 2 decades. They'd spent years developing theoretical models of what the early universe should look like. They knew what they expected to see. Small, primitive galaxies struggling to form in the cosmic darkness. A young universe slowly assembling its first structures. Black holes that were just beginning to grow. A cosmos that matched our equations and predictions. That's not what Webb showed them. The very first deep field image revealed something shocking. The early universe was full of galaxies. Not just a few scattered objects. Hundreds of them. Bright, massive, fully formed galaxies shining across the first few 100 million years after the Big Bang. This shouldn't have been possible. In our standard models, galaxies grow slowly. They start small, perhaps just a few million stars clustered together. Over hundreds of millions of years, they collide and merge with other small galaxies. They accumulate more gas. They form more stars. Eventually, after billions of years, they become the grand spiral and elliptical galaxies we see in the nearby universe. But Webb was seeing galaxies that had skipped this process entirely. Just 280 million years after the Big Bang, a galaxy called MOM Z14 appeared. Think about that timeline. The universe began 13.8 billion years ago in the Big Bang. 280 million years sounds like a long time. But in cosmic terms, it's nothing. It's 2% of the universe's current age. If the universe's entire history were compressed into a single year, this galaxy formed on January 5th. The Big Bang happened at midnight on January 1st. By January 5th, this galaxy already existed, already shining, already forming stars. To understand how shocking this is, you need to know what the universe looked like right after the Big Bang. In the beginning, there were no galaxies, no stars, no planets. not even atoms. The universe was filled with an incredibly hot, incredibly dense mix of elementary particles. Quarks and electrons and photons, all bouncing off each other in a cosmic fireball. For the first 380,000 years, the universe was opaque. Light couldn't travel freely because it kept scattering off charged particles. This era is called the Dark Ages, though that's a misnomer because the universe was actually glowing with intense radiation. It was just that the radiation couldn't escape to travel across space. Everything was trapped in this dense, hot fog. Then, as the universe expanded and cooled, something crucial happened. Protons and electrons combined to form neutral hydrogen atoms. This is called recombination. When it happened, light could suddenly travel freely. The universe became transparent. The cosmic microwave background radiation we see today is the afterglow from this moment, light that's been traveling across the universe ever since. But even after recombination, there were still no stars. The universe was filled with neutral hydrogen gas, cooling and expanding. Gravity started pulling this gas together into denser clumps. These clumps eventually became the seeds of the first stars. But this process takes time. The standard models predicted it would take at least 100 million years for the first stars to form, maybe 200 million. Those first stars, called population 3 stars, would be massive and short-lived. They'd burn through their fuel quickly, perhaps in just a few million years. When they died, they'd explode as supernovae, scattering the first heavy elements across space. Those heavy elements would mix with the pristine hydrogen gas. The next generation of stars would form from this enriched material. They'd live longer and form more varied types of stars. Over hundreds of millions of years, stars would cluster together into the first small galaxies. These proto-galaxies would be tiny compared to modern galaxies. Perhaps a few million stars instead of hundreds of billions. They'd collide and merge with other small galaxies. Gradually, through countless mergers and accretion of gas, they'd grow into the massive galaxies we see in the nearby universe. This process was supposed to be slow, gradual, a steady progression from simple to complex. MOM-Z14 breaks this timeline because, at 280 million years after the Big Bang, this galaxy wasn't small. It wasn't primitive. MOM-Z14 was already massive, already forming stars at an incredible rate, already chemically enriched with heavy elements that should have taken generations of stars to produce. The galaxy contained oxygen, nitrogen, carbon. These elements don't exist in the pristine hydrogen and helium that filled the early universe. They're created inside stars through nuclear fusion. When massive stars explode as supernovae, they scatter these elements across space. The next generation of stars incorporates them. Over many generations, galaxies gradually become enriched with heavier elements. This is a slow process. It requires multiple cycles of star formation and death. Yet MOM-Z14, existing just 280 million years after the Big Bang, was already showing high levels of nitrogen enrichment. This shouldn't have been possible in the available time. There's a theory that the dense environment of the very early universe might have allowed the formation of supermassive stars. Stars millions of times the mass of our Sun. These hypothetical giants would burn incredibly hot and die incredibly fast. In their brief lifetimes, they might produce enormous amounts of heavy elements. When they collapsed, they wouldn't go through the normal supernova process. They'd collapse directly into massive black holes. If such stars existed, they could explain both the rapid chemical enrichment and the rapid black hole growth we're observing. But we've never seen a supermassive star. They're theoretical constructs based on extreme conditions we think might have existed in the early universe. Seeing evidence of their effects in galaxies like MOMZ-14 is tantalizing. It suggests these monster stars might actually have existed, that the early universe was capable of creating objects unlike anything we see today. Rohan Naidu, the astronomer who confirmed this discovery, said something remarkable. With Webb, we are able to see farther than humans ever have before, and it looks nothing like what we predicted. Nothing like what we predicted. That's the key phrase. This wasn't a small discrepancy. This wasn't a galaxy that was slightly bigger than expected or appeared slightly earlier than models suggested. This was a fundamental mismatch between theory and observation. The galaxies Webb found were 100 times more abundant than theoretical studies had predicted before the telescope launched. 100 times more. Imagine building a telescope expecting to find 10 objects and instead finding 1,000. That's not a minor adjustment to your models. That's evidence that something fundamental is wrong with your understanding. And MOMZ-14 wasn't alone. Webb kept finding these impossibly early, impossibly bright galaxies. Galaxy after galaxy appearing in the first few 100 million years. Each one a challenge to our cosmological models. Each one demanding an explanation. Scientists started calling this the growing chasm between theory and observation. We have equations that describe how the universe evolves. We have simulations that model how the first structures form. We have decades of astronomical data supporting these models. And now we have direct observations showing that those models are incomplete. Something happened in the early universe that we don't understand. Some process allowed galaxies to form faster, to grow larger, to become more complex than our physics predicts. And it's not just one or two anomalies. It's systematic. It's everywhere Webb looks. But the mystery gets deeper. Because the galaxies themselves aren't the only problem. Let's talk about what's inside them. At the heart of most large galaxies sits a supermassive black hole. These aren't the stellar mass black holes formed when massive stars collapse. These are monsters. Black holes containing millions or billions of times the mass of the Sun. Our own Milky Way has one. Sagittarius A. 4 million solar masses sitting at the galactic center. For decades, astronomers have known these supermassive black holes exist. But we've never fully understood how they form or how they grow so large. The problem is time. Black holes grow by accreting matter. Gas and dust fall into them. Stars pass too close and get torn apart. Smaller black holes merge together. But this process has limits. There's a maximum rate at which a black hole can consume matter, called the Eddington limit. This isn't an arbitrary restriction. It's fundamental physics. When material falls toward a black hole, it doesn't plunge straight in. It forms an accretion disk, a swirling mass of gas and dust spiraling inward. The material in this disk rubs against itself, creating enormous friction. This friction heats the gas to millions of degrees. At these temperatures, the gas emits intense radiation, primarily X-rays and ultraviolet light. This radiation exerts pressure. Photons, particles of light, carry momentum. When they hit atoms in the infalling gas, they push the atoms outward. If the black hole tries to consume matter too quickly, the radiation pressure becomes so strong that it blows the infalling material away. This creates a natural speed limit. You can't just dump unlimited matter into a black hole. The black hole's own radiation creates a barrier. The Eddington limit defines the maximum luminosity a black hole can emit while still being able to accrete matter. For a black hole of a given mass, there's a maximum accretion rate. If you exceed it, the radiation pressure becomes too strong and prevents further accretion. This means black hole growth is fundamentally limited by physics. A black hole can only double its mass every few tens of millions of years if it's feeding at the Eddington limit. Most black holes don't feed at the Eddington limit. They feed at a fraction of that rate because there isn't enough matter nearby, or because outflows and jets remove energy from the system, or because the supply of infalling material is intermittent. This is why the supermassive black holes in the early universe are so puzzling. Even if a black hole formed immediately after the Big Bang, which is probably impossible, and consumed matter at the absolute maximum rate allowed by physics, continuously for hundreds of millions of years, it still couldn't reach 1 billion solar masses. The math simply doesn't work. Give a stellar mass black hole, say 100 solar masses, 500 million years to grow at the Eddington limit. It reaches perhaps 100,000 solar masses, still far short of 1 billion. To get to 1 billion solar masses in that time frame, you'd need to start with a much more massive seed. Or you'd need to exceed the Eddington limit substantially. Or both. This creates a fundamental problem for cosmologists. But Webb found black holes that broke these rules. Just 500 million years after the Big Bang, in a galaxy called Kuiper's LRDZ9, Webb detected a supermassive black hole weighing 300 million solar masses. Let me repeat that. 500 million years after the universe began, a black hole already contained the mass of 300 million suns. This black hole comprises half the mass of all the stars in its entire galaxy. It's not just at the center of the galaxy. It's dominating the galaxy's mass budget. And it's growing rapidly, consuming matter far faster than we thought possible. Astronomers found this black hole wasn't alone either. Webb surveyed 25 early quasars, the brilliant beacons powered by actively feeding supermassive black holes. The black holes at their centers ranged from 600 million to 2 billion solar masses, all of them existing less than 1 billion years after the Big Bang. All of them impossibly massive for their age. This presents cosmologists with a profound problem. How do you make 1 billion solar mass black hole in less than 1 billion years? The traditional model doesn't work. In the standard picture, the first stars form perhaps 100 million years after the Big Bang. Some of these stars are massive, perhaps 100 solar masses. They burn bright and die young, collapsing into black holes weighing tens or hundreds of solar masses. These seed black holes then grow slowly over cosmic time, accreting matter and merging with other black holes. Eventually, after billions of years, they become the supermassive monsters we see today. But this process is too slow. Even if you start with a 100 solar mass black hole and let it feed at the maximum rate allowed by physics, you can't get to 1 billion solar masses in 500 million years. The math doesn't work. So scientists have proposed alternatives. Maybe the first black holes didn't come from stars at all. Maybe they formed through direct collapse. In this scenario, enormous clouds of pristine hydrogen gas, hundreds of thousands of solar masses, collapse directly into black holes without ever forming stars. This would create seed black holes that start out massive, perhaps 10,000 to 100,000 solar masses. With that head start, they might have time to reach 1 billion solar masses. But direct collapse requires very specific conditions. The gas must be incredibly dense, but also very hot, preventing it from fragmenting into stars. And it's not clear these conditions existed widely in the early universe. Another possibility involves the very first generation of stars. These stars, called population 3 stars, formed from gas that contained only hydrogen and helium. No heavy elements. Without heavy elements to cool the gas efficiently, these first stars might have grown to truly monstrous sizes. Not 100 solar masses. 10,000 solar masses. 100,000 solar masses. Maybe even 1 million solar masses. When such a hypermassive star collapses, it would create a black hole of equivalent mass. Again, a head start that might explain the rapid growth. But we've never actually seen a population 3 star. They're theoretical. And recent simulations suggest that even in the pristine early universe, gas fragmentation would prevent such enormous stars from forming. A third option is that black holes in the early universe somehow exceeded the Eddington limit. Maybe in the dense, chaotic environment of the first galaxies, radiation couldn't escape as efficiently as our models predict. Maybe thick shrouds of gas trapped the radiation, allowing black holes to feed at rates 10 or even 40 times faster than normal. This is called super Eddington accretion, and Webb has found evidence it might be happening. Some early black holes show signatures of consuming matter at extraordinary rates, far beyond what should be possible. But even super Eddington accretion has limits. Push it too far, and the physics breaks down in ways we don't understand. Then there's the possibility that involves mergers. Maybe the early universe was full of medium-sized black holes, perhaps 10,000 solar masses each. Maybe these black holes merged repeatedly in the dense environments of early galaxy clusters. Merge enough of them together fast enough, and you could build a supermassive black hole quickly. But this requires an incredible number of mergers happening in a very short time. And each merger produces gravitational waves that carry energy away, actually slowing down the growth process. The truth is, we don't know. Each explanation has problems. Each requires conditions or processes that we haven't confirmed. What Webb is showing us is that one or more of these exotic formation pathways must have operated in the early universe. Because the black holes are there. We can see them. We can measure their masses. They exist, whether or not our theories can explain them. And here's what makes this particularly uncomfortable for cosmologists. These black holes aren't rare oddities. They're common. Everywhere Webb looks in the early universe, it finds supermassive black holes that grew too fast. This suggests that rapid black hole growth wasn't some occasional anomaly. It was the norm, the standard process, the way things actually worked in the first billion years. Our models, built on observations of the nearby universe, assumed the same physical laws operated the same way in the distant past. But maybe they didn't. Maybe the early universe was fundamentally different in ways we're only now beginning to understand. But wait, it gets stranger. Because it's not just the galaxies themselves or the black holes inside them. It's the way they're arranged. The cosmic web. If you could zoom out far enough to see the universe on its largest scales, you'd notice something remarkable. Galaxies aren't randomly scattered through space, like stars thrown across the night sky. They're organized into an intricate pattern, a structure so vast it defies easy comprehension. Imagine a three-dimensional spider web stretching across billions of light years. The threads of this web are filaments, narrow structures made primarily of dark matter with galaxies forming like dewdrops along their length. Where multiple filaments intersect, you find clusters containing hundreds or thousands of galaxies. Between the filaments lie vast cosmic voids, enormous volumes of space that are nearly empty. These voids can be hundreds of millions of light years across. They contain very few galaxies, very little matter, almost nothing at all. Just empty space, expanding as the universe grows. This entire structure, the filaments and clusters and voids together, is what astronomers call the cosmic web. It's the largest scale pattern in the universe. Nothing is bigger or more organized than this. Understanding how this web forms is crucial to understanding cosmic evolution. The process begins in the very early universe, shortly after the Big Bang. The cosmic microwave background shows us that at 380,000 years after the Big Bang, the universe was remarkably smooth. The density of matter varied by only about 1 part in 100,000, almost perfectly uniform. But those tiny variations, those 1 part in 100,000 differences in density, were the seeds of all future structure. Regions that were slightly denser had slightly stronger gravity. They pulled in matter from their surroundings. This made them denser still, which increased their gravity further, which pulled in even more matter. Meanwhile, regions that were slightly less dense lost matter to their denser neighbors. They became even emptier. Over time, this process amplified the initial tiny variations. Dense regions condensed into filaments and clusters. Empty regions expanded into vast voids. By about 1 billion years after the Big Bang, the cosmic web should have been emerging. Filaments should have been forming. The first clusters should have been assembling. But the structure should still have been subtle, early, still in the process of organizing itself. Our simulations show this clearly. When you model the evolution of the universe from the Big Bang forward, using our best understanding of dark matter and gravity, the cosmic web appears gradually. It's not there at 500 million years. It's barely visible at 800 million years. By 1 billion years, you start to see hints of filamentary structure. By 2 billion years, the web is becoming clear. By 5 billion years, it looks much like what we see in the nearby universe today. This is the prediction. This is what should happen, based on our understanding of how gravity works and how matter clusters. Webb is seeing something different. Just 830 million years after the Big Bang, astronomers using Webb found a cosmic filament stretching 3 million light-years across space. 3 million light-years. That's enormous, even by cosmic standards. The Milky Way is about 100,000 light-years in diameter. This filament is 30 times longer than our entire galaxy is wide. And it's not just a vague overdensity of galaxies. It's a well-defined structure. A thin line of 10 galaxies arranged in a diagonal formation across Webb's field of view. The galaxies are aligned. They're connected. gas flows between them along the filament. The structure is anchored on one end by an incredibly bright quasar, a supermassive black hole actively feeding and shining with the light of trillions of suns. Feige Wang, the astronomer who discovered this filament, expressed genuine surprise. This is one of the earliest filamentary structures that people have ever found associated with a distant quasar. The shock in that statement is subtle but profound. This isn't just early. It's organized. It's mature. It's what astronomers expect to see billions of years later, not hundreds of millions of years after the Big Bang. The filament exists at a time when the cosmic web was supposed to be just forming, when structure should have been subtle and poorly defined. Instead, here's a clear, obvious, fully assembled filament. And it's not alone. Webb keeps finding these structures. Protoclusters, where dozens of galaxies are already gathered together, dense knots in the cosmic web that look like they've been evolving for billions of years. Galaxy groups, showing evidence of multiple past interactions. All of this happening in the first billion years of cosmic history. One particularly striking discovery involved a merger of at least 5 galaxies occurring just 800 million years after the Big Bang. This wasn't a gentle coming together. This was a violent collision. Multiple galaxies, each containing billions of stars, crashing together. Their gas clouds colliding at enormous speeds. Shock waves compressing the gas and triggering bursts of star formation. Gravitational forces tearing at the galaxy's structures. The merger was producing new stars at a rate equivalent to about 250 solar masses per year. For comparison, the Milky Way currently produces about 1 or 2 new solar masses worth of stars per year. This early merger was outproducing our entire galaxy by a factor of more than 100. And surrounding the merging galaxies was something unexpected. A halo of enriched gas. Gas that glowed with the signatures of ionized oxygen and hydrogen. This gas wasn't inside the galaxies. It was spread across the space between them. Tens of thousands of light years from the nearest galaxy. How did it get there? The oxygen had to be produced inside stars through nuclear fusion. When those stars died, some as supernovae, the oxygen was expelled into space. But the distribution of this enriched gas suggested something beyond normal stellar winds. The researchers determined that the galaxy merger itself was responsible. The gravitational interactions during the collision flung gas out of the galaxies and into the surrounding space. This was direct evidence that mergers in the early universe weren't just assembling galaxies. They were also enriching the intergalactic medium, the gas between galaxies, with heavy elements. They were shaping the chemical composition of the cosmic web itself. This has profound implications for how we understand galaxy evolution. In the nearby universe, we see evidence of past mergers. Galaxies with distorted shapes. Tidal streams of stars pulled out by gravitational interactions. Chemical signatures showing that different stellar populations merged together. But these are the aftermath of mergers that happened billions of years ago. Webb is showing us the mergers in action. In real time, frozen in light that's been traveling toward us for over 13 billion years. We're seeing how galaxies actually collide, how they mix their contents, how they trigger star formation, how they redistribute elements across vast distances. And we're seeing it happen far earlier than we expected. At a time when galaxies should still be small and isolated. at a time when the cosmic web should barely exist. Yet, here are 5 galaxies colliding violently, embedded in a larger structure of hundreds of other galaxies, all organized into an emerging filament of the cosmic web. The density of galaxies in these early structures is startling. In the nearby universe, galaxies are separated by millions of light years, on average. Our nearest large neighbor, Andromeda, is about 2.5 million light years away. That's relatively close by cosmic standards, and Andromeda and the Milky Way are on a collision course, though they won't actually merge for another 4 billion years. But in the early universe, as seen by Webb, galaxies were packed much more tightly, hundreds of thousands of light years apart instead of millions. This meant interactions were far more common. Collisions happened frequently. The mergers that build large galaxies occurred rapidly, and the cosmic web assembled quickly because there was less distance for structure to span. Everything was happening in fast forward. Not because the physics was different, but because the environment was different. The early universe was smaller, denser, more dynamic. Galaxies formed faster because they had access to more gas. Black holes grew faster because there was more matter nearby to consume. The cosmic web assembled faster because gravity had less distance to work across. And all of this was happening in an environment we can never recreate or fully simulate. We can model it. We can run computer simulations of the early universe. But our simulations are approximations. They make assumptions about gas physics, about star formation efficiency, about how dark matter clusters. They can't capture every detail of every interaction. What Webb is doing is showing us what actually happened, not what our models predict should have happened. What actually did happen in the real universe 13 billion years ago. And the real universe assembled its structures faster, more efficiently, more completely than our simulations suggested was possible. Just 830 million years after the Big Bang, astronomers found a cosmic filament stretching 3 million light-years across space. Not a subtle hint of structure. A fully formed filament containing 10 galaxies arranged in a thin, distinct line. Feige Wang, the astronomer who discovered it, said this is one of the earliest filamentary structures that people have ever found. The surprise isn't just that it exists, it's how well defined it is. This filament is anchored by a brilliant quasar on one end, a supermassive black hole shining across cosmic time. The galaxies along the filament are aligned, organized, connected by flows of gas and dark matter. This is mature structure. This is what we expect to see billions of years later, not hundreds of millions of years after the universe began. And it's not unique. Webb keeps finding these early cosmic structures, protoclusters, where multiple galaxies are already interacting. Massive galaxy collisions happening when the universe was less than 1 billion years old. In one discovery, astronomers found a merger involving at least 5 galaxies occurring just 800 million years after the Big Bang. 5 galaxies colliding, not drifting slowly toward each other, actually merging, with gas and stars being redistributed by gravitational interactions. The team found enriched gas surrounding these galaxies. Oxygen and other heavy elements spread across tens of thousands of light years. This gas had been expelled from the galaxies by the violence of the collision. But here's what makes this significant. That enriched gas proves the galaxies had already gone through generations of star formation before the merger. Stars had formed, lived, and died, producing heavy elements. Those elements were incorporated into new generations of stars. And now the merger was spreading those elements across intergalactic space, enriching the cosmic web itself. All of this happened in less than 1 billion years. Our models predicted the early universe would be simple. Small galaxies forming in isolation. Gradual growth over cosmic time. The cosmic web slowly assembling as structure emerged from chaos. Instead, Webb is showing us an early universe that was remarkably organized. Galaxies were already clustered. The cosmic web was already defined. Large-scale structure existed when it shouldn't have. This matters because structure formation is tied to dark matter. Dark matter makes up about 85% of all matter in the universe. We can't see it directly, but we can observe its gravitational effects. And the cosmic web is fundamentally a dark matter structure. Ordinary matter, the stuff that makes stars and planets, and us, follows the gravitational framework laid down by dark matter. If the cosmic web formed faster than predicted, it means dark matter clustered faster than our models suggest. And that has implications for our understanding of what dark matter actually is. Some astronomers have proposed that the elongated shapes of early galaxies might be evidence for alternative dark matter models. Instead of cold dark matter, which clumps tightly and creates relatively smooth filaments, maybe the universe contains warm or wave dark matter. These hypothetical forms of dark matter would create smoother, more coherent filaments that could feed galaxy formation more efficiently. Gas would flow along these filaments in steady streams, building elongated galaxies quickly. This is speculative. The evidence isn't conclusive. But it shows how Webb's discoveries are challenging not just our models of galaxy formation, but our understanding of the fundamental components of the universe. Now, let me show you something truly strange. Among all the unusual objects Webb has found, there's a class that has scientists particularly puzzled. They're called little red dots. The name is almost comically simple for objects that might represent some of the most exotic phenomena in the universe. These are small, extremely distant objects that appear as tiny red points in Webb's images. At first glance, they seem unremarkable, just faint red dots scattered across the deep field images. But when astronomers examined them closely, when they took spectra and measured their properties, they realized these objects were anything but ordinary. These little red dots are extremely compact, far smaller than typical galaxies. Some are only a few hundred light-years across. That's tiny by galactic standards. The Milky Way is 100,000 light-years in diameter. These objects are 1,000 times smaller. Yet, they're incredibly bright. Far brighter than they should be for their size. A small region of space, only a few hundred light-years across, shining with the light output of an entire galaxy. This suggests something extremely energetic is happening in a very confined space. When astronomers examined the spectra, they found signatures that didn't match standard galaxies. The light showed evidence of extremely hot gas. Gas heated to temperatures of tens of thousands of degrees or more. This could indicate the presence of an active black hole. Supermassive black holes, when they're actively feeding, heat the surrounding gas to extreme temperatures. The gas emits characteristic wavelengths of light that reveal its composition and temperature. Many little red dots show these signatures. They appear to contain actively accreting black holes at their cores. But here's where it gets strange. The black holes would have to be incredibly massive relative to the size of their host galaxies. In normal galaxies, there's a relationship between the mass of the central black hole and the mass of the galaxy's stars. The black hole typically comprises about 0.1% of the stellar mass. Sagittarius A, the Milky Way's central black hole, follows this relationship closely. It's about 4 million solar masses. The Milky Way contains about 200 billion solar masses of stars. 0.1% of 200 billion is about 200 million. Our black hole is actually smaller than average. But in the little red dots, this relationship appears broken. The black holes seem to comprise a much larger fraction of the total mass, perhaps 10% or more. They're not just at the center of their host galaxies. They're dominating the mass budget. Some little red dots show additional peculiar features. Their spectra contain emission lines that suggest the presence of extremely massive stars. Not just massive by normal standards. Truly enormous stars. Millions of solar masses each. This has led some astronomers to propose a radical idea. Maybe the little red dots aren't galaxies with black holes at all. Maybe they're black hole stars. A black hole star would be a theoretical object, unlike anything we've ever observed. Imagine a star so massive that it collapses to form a black hole at its core while still in the process of forming. The outer layers of the star continue to accumulate mass and burn through nuclear fusion. But the inner core has already collapsed into a black hole. The black hole consumes matter from the inside, growing larger. The star continues to shine from the outside, powered by fusion in its envelope. The result would be a hybrid object. Part star, part black hole. It would be incredibly compact because the mass is concentrated in the black hole at the center. It would be incredibly luminous because the infalling matter and the fusion in the envelope both produce enormous amounts of energy. And it would have a very short lifetime. Such an object would be fundamentally unstable. The black hole would consume the star from within, over perhaps just a few million years. When it finished, you'd be left with a supermassive black hole seed. A black hole that started out weighing millions of solar masses instead of tens or hundreds. This could solve the puzzle of how supermassive black holes grew so quickly. If black hole stars existed in the early universe, they would create massive seed black holes that could then grow to billions of solar masses through normal accretion. You wouldn't need to violate the Eddington limit. You wouldn't need exotic formation mechanisms. You just need these massive seeds. But black hole stars have never been observed. They're purely theoretical, derived from models of stellar collapse under extreme conditions. Conditions that might have existed in the dense, turbulent environment of the very early universe, but don't exist anywhere in the cosmos today. Until Webb found the little red dots. Now, astronomers are seriously asking whether these strange objects might be black hole stars. Whether we're seeing these exotic theoretical constructs actually existing in the early universe. Whether we've found direct evidence of how supermassive black holes were born. Another interpretation suggests the little red dots might be powered by dark matter. In this scenario, they're not black hole stars, but dark stars. Dark stars would form in the very first halos of dark matter that condensed out of the primordial universe. When hydrogen and helium gas falls into these dark matter halos and begins to collapse, dark matter particles in the core might annihilate each other. Dark matter annihilation releases enormous amounts of energy. This energy would heat the gas, preventing it from collapsing all the way to form a normal star. Instead, you'd get a dark star, an extended envelope of hydrogen and helium held up by the energy from dark matter annihilation. These dark stars could grow to enormous sizes, millions of solar masses, even billions. They'd be incredibly luminous, powered not by nuclear fusion, but by dark matter physics. And they'd be stable as long as they had a supply of dark matter particles to annihilate. Eventually, the dark matter would be depleted. The annihilation would stop, and the dark star would collapse into a supermassive black hole. Again, creating a massive seed that could then grow through accretion. This is speculative. Dark stars are even more theoretical than black hole stars. We don't even know for certain what dark matter is, let alone whether it can power exotic stars. But the little red dots are so strange that astronomers are considering every possibility. Some little red dots might be black hole stars. Others might be dark stars. Others might be something we haven't thought of yet. Or they might be extreme examples of normal galaxies and black holes, just forming under conditions so different from what we're used to that they produce signatures we don't recognize. One thing is certain. The little red dots represent a phase of cosmic evolution we didn't know existed. They're showing us objects and processes that have no modern analogues. Things that happened only in the first few 100 million years of the universe's existence. Things that can never happen again because the conditions that created them no longer exist. And we're seeing them now, in Webb's images, frozen in light that's been traveling across the universe for over 13 billion years. These objects existed briefly, evolved, and then either became normal galaxies or collapsed into black holes. Their era ended billions of years ago. But the light from that era is arriving now, giving us a window into cosmic history we've never had before. A window into the exotic physics and extreme conditions of cosmic dawn. And here's something that should unsettle you. We're racing against time to study these objects. Not in a human timescale, though there is some urgency in that sense too, but in a cosmic timescale. A race against the expansion of the universe itself. Let me explain something fundamental about observation and cosmology. The universe is expanding. This has been known since 1929, when Edwin Hubble measured the distances and velocities of galaxies and found they were all moving away from us. The farther away a galaxy was, the faster it was receding. This wasn't because galaxies were physically moving through space. It was because space itself was expanding, carrying the galaxies with it. Imagine a balloon with dots marked on its surface. As you inflate the balloon, the dots move apart from each other. Not because they're moving across the rubber, but because the rubber itself is stretching. The universe works the same way. Galaxies sit in space, and space itself expands, increasing the distances between galaxies. This expansion has profound effects on light. When light travels from a distant galaxy toward us, it's traveling through expanding space. As space expands, the light waves get stretched along with it. Stretched waves have longer wavelengths. For visible light, longer wavelengths mean redder colors. This is why we call it redshift. A galaxy's light literally shifts toward the red end of the spectrum as it travels through expanding space. The farther the light has to travel, the more space expands during its journey, the more the light gets redshifted. Astronomers use redshift as a distance indicator. High redshift means the light has traveled a long distance through expanding space. Low redshift means it hasn't traveled as far. The most distant galaxies Webb observes have redshifts of 14 or even higher. This means their light has been traveling for over 13 billion years. It left those galaxies when the universe was very young, just a few 100 million years old. And during its 13 billion year journey, the expansion of the universe stretched that light dramatically. Light that was emitted as ultraviolet or visible light is arriving as infrared. This is why Webb needs infrared detectors to see these distant galaxies. Their light has been redshifted completely out of the visible spectrum. But here's the unsettling part. The universe isn't just expanding. It's accelerating. In the late 1990s, two teams of astronomers were studying distant supernovae. These supernovae, Type 1, a supernovae, have a consistent brightness. This makes them useful as standard candles for measuring cosmic distances. By comparing how bright they appear to how bright they should be, you can calculate how far away they are. Both teams found something unexpected. The most distant supernovae were fainter than they should be. This meant they were farther away than the expansion rate would predict. The only explanation was that the expansion of the universe had sped up over time. Something was accelerating cosmic expansion. The teams called this something dark energy, and it revolutionized cosmology. We still don't really know what dark energy is. It's not matter. It's not radiation. It's some property of space itself that causes expansion to accelerate. The best measurements suggest dark energy comprises about 70% of the total energy density of the universe. It's the dominant component, and it's causing the universe to expand faster and faster as time goes on. This acceleration has consequences for observation. As the universe expands and accelerates, distant objects move away from us faster and faster. Eventually, objects become so distant that they're moving away faster than the speed of light. This sounds like it violates relativity, but it doesn't. Relativity says nothing can move through space faster than light. But space itself can expand at any rate. Objects can be carried apart by expanding space at faster than light speeds without actually moving through space. When this happens, when an object's recession velocity exceeds the speed of light, its light can never reach us. The light tries to travel toward us, but the space between us and that object is expanding faster than light can cross it. The light is like someone running the wrong way on a treadmill that's moving faster than they can run. They can run forward, but they're still moving backward. This creates a boundary called the cosmic horizon. Beyond the cosmic horizon are galaxies whose light will never reach us. Not because they don't exist. They do. But because the expansion of space prevents their light from ever arriving, currently, the observable universe extends about 46 billion light-years in every direction. This seems contradictory at first. If the universe is 13.8 billion years old, and light travels at a fixed speed, shouldn't the observable universe only extend 13.8 billion light-years? No, because space has been expanding while light was traveling. A galaxy 13 billion light-years away, when it emitted, the light we're now seeing has since moved much farther away due to cosmic expansion. By the time its light reaches us, that galaxy is now about 46 billion light-years away. So the observable universe is a sphere 93 billion light-years in diameter, centered on Earth. That's everything we could possibly observe, even in principle. But beyond that sphere lies more universe. How much more? We don't know. The universe might extend another 93 billion light-years beyond the horizon and then end. Or it might extend for thousands of times that distance. Or it might be infinite, stretching endlessly in all directions. We have no way to know because we can't observe anything beyond the cosmic horizon. Those regions exist, but they're permanently inaccessible to our observations. And here's the truly unsettling part. The cosmic horizon is moving. Not outward, inward. Well, it's complicated. In terms of physical distance, the horizon is actually moving outward as the universe expands. But in terms of which objects we can observe, the horizon is effectively shrinking. Because of accelerating expansion, objects that we can see today will eventually cross beyond the horizon. Their recession velocity will exceed light speed. Their light will no longer be able to reach us. They'll fade from view, not because they've disappeared, but because the space between us and them is expanding too fast for light to cross. Give it enough time, trillions of years, and the only galaxies we'll be able to see will be those gravitationally bound to our local group. The Milky Way and Andromeda will have merged by then into a single large elliptical galaxy. A few dozen smaller satellite galaxies will remain bound to this merged galaxy. And that's it. Everything else will have receded beyond the horizon. The cosmic microwave background, the afterglow of the Big Bang, will have been redshifted beyond any possible detection. The evidence of cosmic expansion will have disappeared. Future astronomers, if they exist, trillions of years from now, will look out at a universe that appears to consist of one island of galaxies surrounded by infinite darkness. They won't be able to see distant galaxies. They won't be able to detect the cosmic microwave background. They won't be able to measure cosmic expansion because everything else will have expanded beyond visibility. They will not be able to deduce that the universe had a beginning. They will not be able to determine the universe's age. All the evidence will have literally expanded beyond the observable universe. This means we live in a special time. A brief window in cosmic history when the universe is old enough to have developed complex structure, including stars and planets and life, but young enough that we can still observe the early universe. The evidence of the Big Bang is still visible. The cosmic microwave background is still detectable. Distant galaxies, showing us cosmic history, are still within our cosmic horizon. This window won't last forever. On cosmic timescales, it's already closing. Not quickly. The changes take billions of years. But it is closing. And the objects Webb is studying, the earliest galaxies and black holes formed in cosmic dawn, are among the most vulnerable to this effect. They're already at the edge of detectability. Their light has been traveling for over 13 billion years. It's been stretched from visible and ultraviolet wavelengths into the infrared. In some cases, into the mid-infrared or even far infrared. Webb can detect this light because it's specifically designed for infrared observation. It has a mirror coated in gold to better reflect infrared light. It has detectors sensitive to infrared wavelengths. It operates at incredibly cold temperatures, just a few degrees above absolute zero, to minimize its own infrared emissions. All of this allows Webb to see galaxies at redshifts of 14 or higher, to observe cosmic dawn in unprecedented detail. But there's a limit. As the universe continues to expand, these galaxies will become even more distant. Their light will redshift even further. Eventually, they'll redshift beyond even Webb's capabilities, beyond the capabilities of any future telescope we can imagine building. Not because of technological limitations, but because of fundamental physics. At some point, the light from these galaxies will be redshifted to wavelengths so long they're indistinguishable from the cosmic microwave background, or they'll be redshifted beyond the wavelengths we can reasonably detect with any instrument. When that happens, these galaxies will effectively disappear from view. Not immediately, not in our lifetimes, or even in the lifetime of human civilization. But eventually, on timescales of billions of years. This means there's a finite window during which we can observe the early universe, a window that opened when the universe became old enough to develop technology and intelligence capable of building telescopes, and a window that will close when expansion pushes the early universe beyond the cosmic horizon. We're living in that window right now, and we're using it to document cosmic dawn before the evidence fades. There's a limit to how far we can see, called the cosmic horizon. Currently, the observable universe extends about 46 billion light-years in every direction. That's a sphere 93 billion light-years across, containing everything we could possibly observe. But most of the universe lies beyond this horizon. Galaxies so far away that their light hasn't had time to reach us yet. And because of accelerating expansion, that light never will reach us. Those galaxies exist, but we can never see them. They're permanently beyond our cosmic horizon. And the horizon is shrinking. Well, not shrinking in an absolute sense. But the fraction of the universe we can observe is decreasing. As expansion accelerates, more and more galaxies cross the boundary from observable to unobservable. Give it enough time, trillions of years, and the only galaxies we'll be able to see will be the ones gravitationally bound to our local group. Everything else will have receded beyond the horizon. Future astronomers, if they exist, will look out at a dark, empty universe. They'll see the Milky Way, Andromeda, and a handful of smaller galaxies. Nothing else. No distant galaxies. No evidence of cosmic expansion. No cosmic microwave background. The universe will appear to be just our local group, surrounded by infinite darkness. Those astronomers won't be able to deduce the Big Bang. They won't be able to measure cosmic expansion. They won't be able to determine the universe's age. All the evidence will have literally expanded beyond their ability to detect it. We live in a special time. A brief window in cosmic history when the universe is old enough to have formed complex structure, but young enough that we can still see evidence of its birth. This window is closing, not quickly by human standards. The changes take billions of years. But it is closing. And the objects Webb is studying, the earliest galaxies and black holes, are among the most vulnerable to this effect. They're already at the edge of detectability. Their light has been traveling for over 13 billion years. It's been stretched from visible and ultraviolet wavelengths into the infrared. Only Webb, with its unprecedented infrared sensitivity, can see them. In a few more billion years, these galaxies will be too distant, too redshifted for any telescope to detect. The evidence of how the first structures formed will be lost. The cosmic web's earliest filaments will fade beyond visibility. The little red dots will disappear from view. The only record of this era will be what we document now. This is why Webb's mission is so urgent. We're documenting a universe that's in the process of hiding itself. We're gathering evidence before it slips beyond the cosmic horizon forever. Think about what this means. Most of the universe already exists beyond what we can observe. There are galaxies out there, vast cosmic structures, phenomena we can't even imagine, all permanently invisible to us because their light will never arrive. The universe is vastly larger than the observable universe. How much larger? We don't know. It could be 1,000 times bigger, 1,000,000 times, infinite. We can never know because we can never see it. This is a profound limitation. It means there are fundamental questions about the universe that we might never be able to answer. Is the universe finite or infinite? We can't tell from within the observable portion. What's the universe's true geometry on the largest scales? We can only measure it within our cosmic horizon. Are there regions where the laws of physics differ? We can't observe them to find out. The universe might be far stranger than we imagine, and we're confined to observing one small bubble within it. But even within that bubble, Webb is revealing surprises. And those surprises are forcing us to reconsider our most fundamental cosmological model. That model is called Lambda CDM. It's worth understanding what this means and why it matters. Lambda is the Greek letter representing the cosmological constant, which Einstein introduced into his equations. He originally added it to keep the universe static, thinking the universe was unchanging. When Hubble discovered cosmic expansion, Einstein called the cosmological constant his greatest blunder. But decades later, when astronomers discovered that cosmic expansion is accelerating, the cosmological constant came back. We now interpret lambda as dark energy, the mysterious force driving acceleration. CDM stands for cold dark matter. This is the invisible matter that provides the gravitational scaffolding for all cosmic structure. It's called cold because the particles move slowly compared to the speed of light, allowing them to clump together to form the cosmic web. Together, Lambda CDM describes a universe composed of several components. About 5% ordinary matter, the stuff that makes stars, planets, and us. About 27% dark matter, providing gravitational structure. About 68% dark energy, driving accelerating expansion. Plus, a small amount of radiation left over from the Big Bang. This model emerged gradually, over decades, as observations accumulated. It explains the cosmic microwave background radiation with incredible precision. The tiny temperature fluctuations in the CMB, the afterglow of the Big Bang, match Lambda CDM predictions to within a few parts per million. It predicts the large-scale structure of the universe, the distribution of galaxies and cosmic voids, the pattern of the cosmic web. When you run simulations, starting from the conditions after the Big Bang and evolving them forward using Lambda CDM, you get a universe that looks remarkably like what we observe. It accounts for the acceleration of cosmic expansion. The distant supernovae observations that revealed this acceleration fit perfectly with a universe dominated by dark energy. It matches the abundances of light elements produced in the first few minutes after the Big Bang. The ratios of hydrogen to helium to lithium match what Lambda CDM predicts based on the density and temperature of the early universe. It explains the rotation curves of galaxies. Galaxies spin in a way that suggests they contain far more mass than we can see in stars and gas. dark matter, distributed in halos around galaxies, provides that missing mass. Lambda CDM has been tested against countless observations from multiple independent sources: radio astronomy, optical telescopes, X-ray satellites, gravitational wave detectors, measurements of distant supernovae, studies of galaxy clustering. All of these different observations, using different techniques and different instruments, point to the same model. Lambda CDM works. It's our standard cosmological model because it successfully explains the vast majority of what we observe about the universe. But, and this is crucial, it's not perfect. No scientific model ever is. All models are approximations of reality, useful for making predictions, but always incomplete in some way. Lambda CDM is no exception. There have been hints for years that something isn't quite right. Small discrepancies that might be measurement errors or might be telling us the model needs refinement. For example, there's the Hubble tension. The Hubble constant describes how fast the universe is expanding. When you measure it using observations of the cosmic microwave background and calculate forward using Lambda CDM, you get one value. When you measure it directly using nearby supernovae and other standard candles, you get a different value. The difference is small, only about 8 to 10%, but it's statistically significant. Multiple independent measurements confirm the discrepancy. Either we're making systematic errors in our measurements, which seems unlikely given how carefully these studies are done, or Lambda CDM is missing something. Some piece of physics that affects the expansion rate. Then there's the core cusp problem. Lambda CDM predicts that dark matter halos should have dense cores, with the density increasing steeply toward the center. But observations of small galaxies suggest their dark matter halos have flatter cores. The density increases more gradually toward the center than Lambda CDM predicts. This could be resolved through better understanding of how gas and star formation interact with dark matter. Or it could suggest that dark matter behaves differently than we think. There are other small tensions. The clustering of matter on small scales doesn't quite match predictions. The number of satellite galaxies around the Milky Way is smaller than simulations suggest there should be. These discrepancies are relatively minor. They don't invalidate Lambda CDM. They suggest refinements might be needed. But Webb's discoveries represent something more substantial. The model predicts galaxy formation should be a slow process, taking hundreds of millions to billions of years. Webb finds fully formed galaxies appearing in just 280 million years. The model predicts black holes should grow gradually, limited by fundamental physics. Webb finds billion solar mass black holes already in place after a few 100 million years. The model predicts the cosmic web should assemble over billions of years as gravity slowly amplifies initial density fluctuations. Webb finds organized filamentary structure already in place within the first billion years. These aren't minor discrepancies. These are systematic differences between what the model predicts and what we observe. Does this mean Lambda CDM is wrong? No. The fundamental framework of the model, dark matter plus dark energy in an expanding universe, still explains the vast majority of cosmological observations. What it means is that Lambda CDM is incomplete when applied to the early universe. There are processes we don't understand, physics we haven't accounted for, conditions in the early universe that differed from what we've assumed. Some scientists have suggested we might need to modify our understanding of dark matter itself. Maybe it's not completely cold. Maybe the dark matter particles have properties we haven't identified. Warm dark matter, where particles move at higher velocities, might cluster differently and create structures faster. Wave dark matter, where quantum effects on large scales influence structure formation, might produce more coherent filaments that efficiently feed galaxy growth. These alternatives to cold dark matter have been proposed for years to address some of the small-scale tensions in Lambda CDM. Now, Webb's discoveries give these ideas new urgency. Maybe the early universe's dark matter behaved differently than it does today. Or maybe the properties of dark matter create effects that only become apparent in the dense environments of the early universe. Others propose that star formation in the early universe was far more efficient than we've assumed. In our models, only a small fraction of available gas converts into stars. The rest is expelled by stellar winds, supernovae, and outflows from active black holes. This inefficiency is built into our simulations based on observations of star formation in nearby galaxies. But maybe the early universe was different. Maybe the dense, metal-poor gas of cosmic dawn formed stars more efficiently. Maybe the first stars formed in bursts rather than steadily, creating pulses of intense star formation. Maybe feedback processes that limit star formation today were less effective in the early universe. If star formation efficiency was higher, by even a factor of 2 or 3, it would dramatically accelerate galaxy growth. Galaxies could assemble much faster than standard models predict. Still, others think the answer lies in feedback processes between different components. The interactions between galaxies, stars, and black holes. In our standard picture, supermassive black holes regulate star formation in their host galaxies. When they actively feed, they produce enormous outflows that heat or expel gas, quenching star formation. This negative feedback prevents galaxies from converting all their gas into stars too quickly. But maybe, in the early universe, black hole feedback operated differently. Maybe, instead of quenching star formation, early black holes actually enhanced it. Their outflows could compress surrounding gas, triggering bursts of star formation. This positive feedback could accelerate both galaxy assembly and black hole growth simultaneously. The black hole grows by accreting gas. Its outflows compress surrounding gas clouds. This triggers intense star formation. The stars evolve and die, some as supernovae that enrich the gas with heavy elements. The enriched gas falls back toward the black hole, feeding it further. The cycle repeats, each time building both the galaxy's stellar mass and the central black hole. This runaway process could explain the rapid coevolution of galaxies and black holes in the early universe. What's clear is that something fundamental about the early universe differed from our standard assumptions. The environment was different. The gas physics was different. The efficiency of structure formation was different. Lambda CDM accurately describes the universe on large scales and at late times. But when applied to the first billion years, it underestimates how quickly structure assembled. It misses some crucial physics or process that dominated during cosmic dawn. Finding that missing piece is now one of the most important challenges in cosmology. And it's not just an academic question. Understanding the early universe has implications for our understanding of dark matter, dark energy, and fundamental physics. If dark matter behaves differently than we think, That changes our understanding of particle physics. Potential dark matter candidates include weakly interacting massive particles, axions, sterile neutrinos, and more exotic possibilities. Each has different properties and would create different observable signatures. Webb's observations might help narrow down which candidates are viable. If star formation operates differently under different conditions, that changes our understanding of galaxy evolution throughout cosmic history. It affects our predictions for how galaxies will evolve in the future. It influences our estimates of how common planets and potentially habitable worlds might be. If feedback processes can create runaway growth under certain conditions, that has implications for understanding other astrophysical systems. It might help explain rapid growth in other contexts, from stellar systems to galaxy clusters. The early universe is a laboratory for extreme physics, conditions that can never be recreated on Earth or even in our local cosmic neighborhood. Densities, temperatures, energies, far beyond anything we can achieve experimentally. By observing what happened under those conditions, we learn about physics in regimes we cannot otherwise access. This is why Webb's discoveries matter so profoundly. They're not just revealing unexpected galaxies and black holes. They're challenging our understanding of fundamental physics. They're showing us that the universe operates in ways more complex than our current models capture. And they're pointing us toward the next generation of cosmological theory. A theory that will incorporate all of Lambda CDM's successes while extending it to explain rapid structure formation in the early universe. And Webb is revealing where it's incomplete. The model predicts galaxy formation should be a slow process. Webb finds fully formed galaxies appearing far too early. The model predicts black holes should grow gradually over cosmic time. Webb finds billion solar mass black holes already in place after a few 100 million years. The model predicts the cosmic web should assemble over billions of years. Webb finds organized filamentary structure in the first billion years. Does this mean Lambda CDM is wrong? No. The model still explains the vast majority of cosmological observations. It's still our best description of how the universe works on large scales. But it's clearly incomplete. There are processes in the early universe that we don't understand, physics that we haven't accounted for. Some scientists have suggested we might need to modify our understanding of dark matter. Maybe it's not completely cold. Maybe it has properties we haven't identified. Others propose that star formation in the early universe was far more efficient than we've assumed. Maybe the first stars formed differently, burned differently, enriched the cosmos differently. Still others think the answer lies in feedback processes. The interactions between galaxies, stars, and black holes might have operated differently when the universe was young and dense. What's becoming clear is that the early universe was not simply a smaller, younger version of today's cosmos. It was fundamentally different, more active, more efficient at forming structure, operating under conditions we don't fully understand. And here's the exciting part. We have the tools to figure this out. Webb is still early in its mission. It's designed to operate for at least 10 years, possibly 20. Every observation reveals new details about the early universe. Every spectrum adds data to refine our models. We're watching cosmology undergo a revolution in real time. The Nancy Grace Roman Space Telescope will launch soon, adding even more capability to survey large areas of the early universe. Ground-based observatories like the extremely large telescope are coming online, providing complementary observations. Gravitational wave detectors might even detect the mergers of the first black holes, giving us a completely different view of this era. We're entering a golden age of early universe astronomy, a time when we can directly observe the first billion years of cosmic history. But we need to understand what we're seeing. And that means confronting the uncomfortable truth that our models aren't complete. It means being willing to revise our understanding based on new evidence. It means accepting that the universe might be stranger, more complex, more interesting than we imagined. Some scientists find this unsettling. They've spent careers building and refining the Lambda CDM model. They've derived its predictions, tested its implications, used it as the framework for understanding everything from galaxy formation to the fate of the universe. Now that framework appears incomplete. Not wrong, but missing crucial pieces. Other scientists find this exhilarating. This is what science is supposed to be: making observations that challenge our theories, finding phenomena that don't fit our models, being forced to think deeper, to question assumptions, to develop new understanding. Every major advance in cosmology has come from observations that didn't match expectations. Hubble's discovery that the universe is expanding, Penzias and Wilson's detection of the cosmic microwave background, the supernova surveys that revealed cosmic acceleration. Each of these observations contradicted prevailing theories. Each forced a fundamental revision of our understanding. And each ultimately led to a deeper, more accurate picture of the cosmos. Webb's discoveries might be the next step in that progression. The observations that force us to develop a more complete cosmological model, one that explains not just the universe today, but how it actually formed in its first billion years. Let me give you some perspective on what we're really looking at. When Webb observes a galaxy from 13 billion years ago, it's seeing light that's been traveling since shortly after the Big Bang. But it's not just seeing an old photograph. It's seeing a moment in time that, for that galaxy, is happening now. The galaxy exists at that moment. The stars are forming. The black hole is growing. The cosmic web is assembling. All of it is real. All of it is happening, frozen in light that's been crossing the universe to reach us. And here's the strange part. That galaxy, in its own time frame, has continued evolving. By now, 13 billion years later, it's probably a massive elliptical galaxy. Its star formation likely stopped billions of years ago. Its supermassive black hole is quiescent, no longer actively feeding. It might be part of an enormous galaxy cluster. But we can't see that. We see it as it was, a young galaxy in a young universe. The information about what it became is traveling toward us, but it won't arrive for billions of years. If we could somehow jump to that galaxy's current location, we'd see an ancient, evolved system. Nothing like the bright young galaxy Webb is observing. This is the nature of astronomical observation. We see the past. The farther we look, the deeper into the past we peer. Webb is giving us a history book of the universe, showing us pages from the earliest chapters. But it's a history book where we can only read the chapters in reverse order, starting with today and working backward. And the earliest chapters, the first few 100 million years, are written in light so faint and so redshifted that only now, with Webb, can we finally read them. What we're discovering is that those early chapters don't tell the story we expected. The universe didn't stumble slowly towards structure. It rushed. It assembled galaxies and black holes and cosmic filaments at a pace that seems impossible by our current understanding. Why? We don't fully know. Here's one possibility that I find particularly interesting. Maybe the early universe was more efficient at forming structures because it was denser. In the first billion years, the universe was much smaller. Everything was closer together. Galaxies were separated by millions of light years instead of hundreds of millions. Dark matter filaments were thicker, denser, more effective at channeling gas. When galaxies collided, which they did frequently in that crowded environment, the collisions were more direct, more violent, more effective at triggering star formation. This higher density might have accelerated everything. Star formation proceeded faster because gas clouds were denser. Black holes grew faster because there was more matter nearby to consume. The cosmic web assembled faster because gravity had less distance to work across. As the universe expanded, these processes slowed down. The density decreased. Galaxies drifted apart. Star formation became less efficient. Black hole growth slowed. The rapid assembly phase ended, and the universe settled into the slower, more gradual evolution we see in more recent cosmic history. This is speculation, but it illustrates how the answer might not require new physics. It might just require us to fully appreciate how different the early universe's environment was from today's. Another possibility involves feedback between different processes. Maybe the first generation of stars created conditions that made the second generation easier to form. Maybe supermassive black holes, once they started growing, accelerated the assembly of their host galaxies through energetic outflows that compressed surrounding gas. Maybe the cosmic web's filaments acted as highways, efficiently funneling gas from vast distances into the densest regions where galaxies were forming. These feedback processes could create a runaway effect. The more structure you have, the more efficiently you create additional structure. The early universe might have crossed a threshold where structure formation suddenly became extremely rapid. And then, as the universe expanded and densities dropped, it fell back below that threshold, returning to the slower formation rate we observe today. Again, speculative. But these are the kinds of ideas scientists are now exploring, because Webb has given them data that demands explanation. Here's what we know for certain. The universe exists. It had a beginning. It's expanding and accelerating. It contains galaxies, stars, planets, and us. All of that is established fact. What we're refining is our understanding of how this all came to be, how structure emerged from the nearly smooth conditions of the early universe, how the first stars ignited, how galaxies assembled, how black holes grew, how the cosmic web formed. Webb isn't disproving the Big Bang. It's not overturning general relativity. It's showing us that the path from the Big Bang to today's universe was more complex than we thought. And that's actually exciting, because complexity means there's more to discover, more physics to uncover, more phenomena to explain. A deeper story about how the universe works. Think about what this means for our place in cosmic history. We exist at a time when the universe is old enough to have formed complex structures, including planets and life, but young enough that we can still observe its early chapters. This isn't just good fortune. It's a narrow window of opportunity. For the first 99.9% of cosmic history, there was no one to observe the universe. No intelligence. No consciousness. No technology capable of building telescopes and decoding the light from distant galaxies. The universe existed, evolved, formed its first structures, but there was no one to witness it. Then, very recently on cosmic timescales, intelligence emerged. Life evolved on at least one planet, possibly many others, and developed the capability to study the cosmos. To build instruments like Webb that can see across billions of light years. To decode the information carried in ancient photons. To reconstruct cosmic history. But this capability appeared at a specific moment. Too early, and the technology wouldn't exist. Too late, and the evidence would have expanded beyond the cosmic horizon. We're living in the narrow overlap, the brief window when both the capability and the evidence exist simultaneously. This window is perhaps a few billion years wide. That sounds like a long time, and by human standards, it is. But in a universe that will exist for trillions of years, possibly infinitely, a few billion years is vanishingly brief. It's less than 1% of the universe's total lifetime. We exist during that 1%. That's remarkable. And we're making the most of it. We exist at a time when technology has advanced enough to build telescopes like Webb that can actually see the first galaxies. Just a few decades earlier, we couldn't have made these observations. The technology didn't exist. Hubble, remarkable as it was, couldn't see far enough into the infrared to observe cosmic dawn in detail. Earlier telescopes couldn't see it at all. The first galaxies were beyond reach, their light too faint and too redshifted to detect. It's only now, with Webb's 6.5-meter mirror and its advanced infrared detectors, that we can finally see these objects. A few decades later, we'll understand what they mean. We'll have refined our models. We'll have identified the missing physics. We'll have solved the mystery of rapid structure formation. But right now, at this very moment in cosmic history, we're at the frontier. We're seeing things we don't fully understand. We're confronting mysteries that challenge our theories. We're living through the moment when cosmology is being revolutionized by direct observations of cosmic dawn. This is rare in the history of science. Most discoveries come incrementally. Small advances building on previous knowledge. Gradual refinement of existing theories. But occasionally, science encounters something truly unexpected. Something that forces a fundamental rethinking of established models. The discovery of cosmic expansion was one such moment. The detection of cosmic acceleration was another. The observation of gravitational waves opened an entirely new window on the universe. Webb's revelations about the early universe might be the next such moment. The observations that force us to develop a more complete cosmological model. We live in interesting times, scientifically speaking. Times of discovery and mystery and revolution in understanding. Times when our knowledge of the cosmos is expanding faster than it ever has before. And we're fortunate enough to be aware of it, to follow these discoveries, to understand, at least conceptually, what they mean, to appreciate that the universe is revealing itself to us in unprecedented ways. This awareness itself is precious. Throughout human history, people have wondered about the cosmos. They've looked up at the night sky and asked questions. Where did everything come from? How old is the universe? What lies beyond what we can see? For most of history, these questions couldn't be answered. They were matters of philosophy or religion, not empirical science. But now, in our lifetime, we're actually answering them. We know the universe had a beginning. We know when it happened. We can observe galaxies forming in the aftermath of that beginning. We can trace the evolution of cosmic structure from the earliest moments to today. We can document the assembly of the cosmos itself. That's extraordinary. And it's happening now, while we're alive to witness it. Every night, Webb points its mirror at the distant universe. Every night, photons that have traveled for billions of years finally reach its detectors. Every night, we gather more data about how the cosmos began. The rate of discovery isn't slowing down either. If anything, it's accelerating. Each new observation reveals something unexpected. Each new spectrum adds to the catalogue of early galaxies and black holes. Each new deep-field image pushes the boundaries of what we can see. Webb is still early in its mission. It launched in December 2021. It began science operations in July 2022. We're still in the first few years of what's designed to be at least a 10-year mission. Possibly 20 years if the telescope remains healthy. That means most of Webb's discoveries are still ahead of us. The galaxies and black holes and cosmic structures we've found so far are just the beginning. As Webb continues to observe, as it surveys more of the sky and examines more distant objects, the catalogue of cosmic dawn phenomena will grow. We'll find even earlier galaxies, even more massive early black holes, even more organized cosmic structure, and each discovery will add to our understanding. Each will provide another constraint on our models. Each will bring us closer to solving the mystery of how structure formed so rapidly in the early universe. We're also developing complementary capabilities. The Nancy Grace Roman Space Telescope is scheduled to launch soon. It will have a field of view 100 times larger than Webb's. While Webb looks deep at small patches of sky, Roman will survey vast areas. Together, they'll give us both depth and breadth. Detailed studies of individual early galaxies from Webb. Statistical studies of large populations from Roman. Ground-based telescopes are advancing too. The extremely large telescope, currently under construction, will have a mirror 39 meters across. That's 6 times the diameter of Webb's mirror. While it can't see as far into the infrared as Webb, it will have unprecedented resolution for objects within Webb's field of view. It will be able to study the internal structure of early galaxies, to map their star-forming regions, to trace the flows of gas and the distribution of dark matter. Gravitational wave detectors are also advancing. The current generation, LIGO and Virgo, can detect mergers of stellar mass black holes. Future detectors, like LISA, will be sensitive to mergers of supermassive black holes. If supermassive black holes in the early universe grew partly through mergers, future gravitational wave observations might detect those ancient merger events, giving us a completely different view of how these objects assembled. All of these instruments together will paint an increasingly detailed picture of cosmic dawn. And somewhere in that picture, we'll find the answer to why structure forms so quickly. But mysteries are meant to be solved. And this one, the mystery of rapid structure formation in the early universe, is within our grasp. And when we find it, when we finally understand how the early universe worked, it will be one of the greatest intellectual achievements in human history. It will be the moment we decoded cosmic dawn, the moment we understood how everything began. Not just abstractly, not just theoretically, but through direct observation of the processes as they happened 13 billion years ago. We're close. The discoveries Webb is making are pieces of the puzzle. Each observation constrains the possibilities. Each measurement rules out some theories and supports others. Slowly, systematically, we're narrowing in on the answer. And the answer, when it comes, will probably surprise us. It usually does. The universe has a habit of being stranger, more intricate, more beautiful than we imagine. Every time we think we understand it, it reveals another layer of complexity, another phenomenon we didn't predict, another process we hadn't considered. That's what makes cosmology exciting. It's not a finished science. It's not a collection of known facts being slowly refined. It's an active frontier where new discoveries constantly challenge our understanding, where the universe keeps showing us things we didn't expect, where every answer generates new questions. Webb is giving us those new questions. How did galaxies form so quickly? How did black holes grow so massive, so fast? How did the cosmic web assemble in the first billion years? What are the little red dots? What processes dominated the early universe that don't operate today? These are fundamental questions about cosmic history, and we're living at the moment when we might finally answer them. Not through speculation, not through theoretical models alone, but through direct observation. Through light that's been traveling across the universe to reach us. Through photons that left distant galaxies when the universe was young and have finally arrived, carrying information about cosmic dawn. That's the power of astronomy. We can't travel to the early universe. We can't go back in time. But we can observe it. We can see it as it was. We can study it in exquisite detail with instruments like Webb. And through those observations, we can reconstruct what happened. We can piece together the story of how the universe evolved from the smooth, simple state after the Big Bang into the rich, complex cosmos we inhabit today. Every galaxy Webb observes adds a page to that story. Every black hole it discovers adds a chapter. Every filament of the cosmic web it reveals adds depth and detail. Slowly, image by image, spectrum by spectrum, we're writing the history of the universe. Not the history we expected. Not the simple, gradual assembly we predicted. But the actual history, the real story of what happened in the cosmos's first billion years. And that story is turning out to be far more dramatic, far more rapid, far more remarkable than we imagined. So, when you hear about Webb's discoveries, when you see images of distant galaxies, or read about supermassive black holes in the early universe, remember what you're really seeing. You're seeing the universe reveal itself. You're seeing evidence that challenges decades of theoretical work. You're seeing the frontier of human knowledge being pushed farther into cosmic history. And you're seeing it at a unique moment in time. A moment when the evidence is still observable. When we have the technology to detect it. When we can still study cosmic dawn before it slips beyond the horizon forever. This is our window. Brief by cosmic standards, but vast by human ones. And we're making the most of it. Every night, Webb points its mirror at the distant universe. Every night, photons that have traveled for billions of years finally reach its detectors. Every night, we gather more data about how the cosmos began. The discoveries aren't slowing down. If anything, they're accelerating. Each new observation reveals something unexpected. Each new galaxy adds to the puzzle. Each new black hole deepens the mystery. But mysteries are meant to be solved. And this one, the mystery of rapid structure formation in the early universe, is within our grasp. The evidence is accumulating. The models are improving. The understanding is developing. Soon, maybe within our lifetimes, we'll have the answer. We'll understand why the early universe was so different. We'll know how galaxies formed so quickly. We'll comprehend how black holes grew so massive. We'll grasp how the cosmic web assembled in record time. And when that happens, when we finally solve this puzzle, it won't be the end of the story. It will be the beginning of the next chapter. Because understanding cosmic dawn will open new questions. It always does. What came before the first galaxies? How did the very first stars form? What happened in the dark ages before the first light? Could there be even earlier structures we haven't detected yet? The universe has layers. Every time we peel one back, we find another beneath. Every answer reveals deeper questions. Every solved mystery exposes new frontiers. That's the nature of cosmology. That's why it's endlessly fascinating. And that's why Webb's discoveries, unsettling as they are to existing models, represent progress. They're showing us what we don't know. They're revealing the gaps in our understanding. They're pointing us toward the next breakthrough. So yes, these discoveries challenge our theories. Yes, they reveal that our models are incomplete. Yes, they force us to confront how much we still don't understand about the universe's earliest moments. But that's exactly what we need. Comfortable agreement with predictions means we're not learning anything new. Surprising disagreement means the universe has more to teach us. And the early universe, as Webb is revealing it, has lessons we never anticipated. It's showing us a cosmos that assembled itself with remarkable speed and efficiency, that formed complex structures in the first few percent of its lifetime, that created galaxies and black holes and cosmic filaments using processes we're only beginning to comprehend. That's not a failure of science. That's science working exactly as it should, making observations, confronting data that doesn't fit expectations, and working to understand what we're really seeing. The universe doesn't care about our models. It doesn't conform to our predictions. It simply exists, operating according to the laws of physics. Our job is to figure out what those laws are and how they work. And sometimes, as Webb is showing us, the universe operates in ways more complex, more interesting, more remarkable than we predicted. That's humbling. It reminds us that despite all we've learned, despite all the progress we've made in understanding the cosmos, we're still students of the universe. Still discovering. Still learning. Still confronting mysteries that challenge our understanding. But it's also inspiring, because it means there's always more to learn, always deeper truths to uncover, always new frontiers to explore. The universe is vast, ancient, and complex. And we, tiny creatures on a small planet orbiting an ordinary star, have developed the capability to observe its earliest moments, to see galaxies forming when the universe was barely born, to watch black holes growing in the cosmic dawn, to map the structure of the early cosmic web, to gather evidence about how everything began. That's extraordinary. That's what makes us human. Not our size or our strength, but our curiosity. Our desire to understand. Our willingness to build telescopes that can see across billions of light years. Our determination to solve mysteries even when they challenge everything we thought we knew. Webb represents the best of that spirit. A telescope built over decades by thousands of people from dozens of countries. A machine designed for one purpose: to see farther and more clearly into the distant universe than ever before. And it's succeeding. Every image it returns expands our knowledge. Every spectrum it captures adds detail to our understanding. Every discovery it makes brings us closer to comprehending how the universe works. The early galaxies Webb is finding aren't anomalies to be explained away. They're data points in the story of cosmic evolution. The supermassive black holes aren't problems for our models. They're evidence of processes we need to understand. The organized cosmic web isn't a contradiction. It's information about how structure forms. All of it is teaching us. All of it is pushing cosmology forward. All of it is part of the grand project of understanding where we came from and how we got here. And we're just getting started. Webb has decades of observations ahead. Other telescopes will join the search. New technologies will enhance our capabilities. The data will keep accumulating. The understanding will keep deepening. The mysteries will keep unfolding. And somewhere in all of that, we'll find the answer. We'll figure out how the early universe worked. We'll understand why structure formed so quickly. We'll comprehend the processes that created the cosmos we observe. And when we do, it will be one of the greatest intellectual achievements in human history. It will rank alongside the discovery of evolution by natural selection, the development of quantum mechanics, the formulation of general relativity, the cracking of the genetic code. These are the moments when humanity fundamentally advanced its understanding of reality. When we decoded some crucial aspect of how the universe works. Understanding rapid structure formation in the early universe will be that kind of achievement. It will tell us something profound about the cosmos, about dark matter, about galaxy formation, about the nature of the first stars and black holes, about physics operating under extreme conditions we can never recreate. It will complete a major chapter in the story cosmology has been writing for the past century. A story that began when Einstein showed that space and time are curved by mass and energy, when Hubble discovered that the universe is expanding, when Penzias and Wilson accidentally detected the cosmic microwave background, when the supernova surveys revealed cosmic acceleration. Each of these discoveries added a page to our understanding. Each brought us closer to comprehending the universe's history and structure. Webb's discoveries are the next pages in that story. The observations that reveal what happened in cosmic dawn, that show us how the universe assembled itself from the nearly smooth conditions after the Big Bang into the rich, complex cosmos we inhabit. And the answer, when it comes, will probably surprise us. It usually does, in science. The universe has a habit of being stranger, more intricate, more ingenious than we imagine. Every time we think we understand something, we discover another layer beneath. Another process we hadn't considered. Another phenomenon that doesn't fit our models. And each time, when we eventually figure it out, the answer is more beautiful and more profound than what we expected. That's what makes cosmology endlessly fascinating. It's not a finished science where we're just filling in details. It's an active frontier where every answer generates new questions, where the universe keeps showing us aspects we didn't anticipate, where our understanding deepens and expands with each generation of observations. Webb is giving us those new questions right now. How did galaxies form so quickly in cosmic dawn? Why were early black holes able to grow so massive in such little time? What created the organized cosmic structure we see in the first billion years? What are the little red dots really showing us? What processes dominated the early universe that don't operate the same way today? These are fundamental questions about the nature and history of the cosmos. We're living at the moment when we have both the technology to observe cosmic dawn and the evidence hasn't yet faded beyond detection. And that brings us back to the beginning, to the question of what scientists were afraid of. It wasn't the observations themselves. Unexpected discoveries are what every scientist hopes for. They're opportunities for progress, chances to learn something genuinely new. What creates discomfort is the realization that our most carefully constructed models are incomplete, that decades of theoretical work and simulation need substantial revision, that fundamental assumptions about the early universe might be wrong. This is intellectually challenging. Scientists have built careers on Lambda CDM. They've written hundreds of papers exploring its implications. They've used it as the foundation for understanding everything from galaxy evolution to the fate of the cosmos. Now they're being told that while the framework is sound, crucial pieces are missing when it's applied to the first billion years. Some find this unsettling. It means going back to the drawing board in some ways, reconsidering assumptions, developing new models, running new simulations, testing new hypotheses. It's hard work, and there's no guarantee of quick success. But most scientists, I think, find this exhilarating rather than frightening. This is what they signed up for. This is why they became cosmologists: to push the boundaries of knowledge, to solve mysteries about the universe, to figure out things that no one has understood before. Webb is giving them the data they need to do exactly that. Yes, the data contradicts some predictions. Yes, it reveals gaps in our understanding, but that's exactly what's needed to make progress. Comfortable agreement with predictions means you're not learning anything new. You're just confirming what you already thought. Surprising disagreement means the universe has more to teach you. It means there are discoveries waiting to be made, processes waiting to be understood, physics waiting to be decoded. And that's exciting. That's the frontier of science. So, while the title of this journey suggests scientists are afraid, I think a better word would be challenged. Webb has challenged cosmology to explain its observations, to account for rapid galaxy formation, to understand early black hole growth, to explain organized cosmic structure in the first billion years. And cosmologists are rising to that challenge. Papers are being published at an extraordinary rate. New models are being proposed. Alternative theories are being tested. International collaborations are forming to tackle these questions. This is science working exactly as it should. Observations drive theory. Theory makes predictions. New observations test those predictions. When observations don't match predictions, theory evolves. We develop better models. We incorporate new physics. We deepen our understanding. And gradually, systematically, we figure out how the universe actually works. Not how we think it should work, how it actually does work, revealed through direct observation and careful analysis. That's the process Webb has accelerated. The telescope is barely 3 years into its mission, and it's already revolutionizing our understanding of cosmic dawn. Imagine what the next 7 years will bring. What the next 20 years could bring if the telescope remains healthy. The catalogue of early galaxies will grow from hundreds to thousands. We'll have statistical samples large enough to distinguish between competing theories. We'll observe rare events and unusual objects that might be crucial to understanding rapid structure formation. We'll push the boundaries even farther back in time, perhaps seeing galaxies at redshifts of 20 or higher. Observing the universe at just 100 million years after the Big Bang, or even earlier. We'll witness cosmic dawn in unprecedented detail. And somewhere in all that data, we'll find the clues we need. The evidence that points to the missing physics. The observations that reveal what processes dominated the early universe. The key to understanding how structure assembled so quickly. This is the promise of Webb's mission. Not just to see the early universe, but to understand it. To solve one of the fundamental mysteries of cosmology. To complete our picture of how the universe evolved from the Big Bang to today. And we're the generation that gets to witness this happening. That gets to follow the discoveries as they're announced. That gets to see cosmology transformed by direct observations of cosmic dawn. Future generations will read about this in textbooks. They'll study the refined models that emerge from Webb's observations. They'll take for granted our understanding of early galaxy formation. But they won't have lived through the discovery process. They won't have experienced the excitement of seeing each new observation, the surprise of finding galaxies that shouldn't exist, the puzzle of black holes that grew too fast, the mystery of organized structure appearing too early, the gradual assembly of clues into a coherent picture. We get to experience all of that. We get to watch it happen in real time. That's a privilege. A remarkable moment in the history of science and human understanding. And it's happening now, in our lifetime, as Webb continues its mission to reveal the cosmos. And when we do, it will be because we didn't look away from the uncomfortable discoveries. We didn't dismiss the data that didn't fit our models. We didn't cling to theories that couldn't explain the observations. Instead, we followed the evidence. We let the universe teach us. We remained open to being surprised, challenged, and humbled by what we found. That's the scientific method. That's how progress happens. That's how we'll solve the mystery of cosmic dawn. Thank you for joining me on this journey through the early universe and the discoveries that are reshaping cosmology. If you found this exploration valuable, a like or subscribe would mean a lot. It helps this channel continue making these deep explorations of space and our place in it. And remember, the universe is revealing itself right now. Every night, Webb is gathering photons from cosmic dawn. Every observation is adding to our understanding. Every discovery is bringing us closer to comprehending how it all began. We live in an extraordinary time, a time when we can see the universe's infancy, when we can study the first galaxies and black holes, when we can watch cosmic structure assembling in the distant past, when we can confront mysteries that previous generations couldn't even imagine. The early universe that Webb is showing us doesn't match our predictions. It's more active, more organized, more complex than we expected. And that's exactly what makes it worth studying. Because the universe we don't understand is infinitely more interesting than the universe we've already figured out. Good night. And may you never stop wondering about the cosmos and our place in it.